All right, let's jump right into it. Hello, focused learners, and welcome to this explainer. Today, we've got a really clear, absolutely crucial goal. We are going to completely demystify linear polynomials. Now, I know if you hear the word polynomial and your brain instantly feels a little, scrambled, do not worry. You are in exactly the right place. We're going to take this step by step. We'll start with something as tangible as a quick shopping trip, and by the time we're done, we'll smoothly transition right into abstract algebraic graphing. You'll see that this isn't just about memorizing some arbitrary rules. It's about learning a powerful new language that literally describes the world around us. So here's our roadmap for today. We're going to hit real-world expressions, decode polynomials, tackle solving equations, look at linear growth and decay, graph those patterns, and then wrap the whole shebang up with a final toolkit. Let's get to it. Section 1. Real-world expressions. Why algebra matters. Okay, let's dive into this. Imagine a student, let's call him Raju, heads to a stationery shop. The owner tells him, look, these sealed red boxes have exactly 4 pens each, and the sealed blue boxes have exactly 5 pencils each. Now, if Raju buys an unknown number of red boxes, let's just call that mystery quantity x. He gets 4 times x pens, right? Or just 4x. And if he buys an unknown number of blue boxes, let's call that y. He gets 5y pencils. Now, what if the shopkeeper is feeling generous and tosses in 3 loose extra pens for free? To find Raju's total haul, we literally just add it all together. 4x plus 5y plus 3. Boom, we have just translated a physical shopping trip into an algebraic expression. The x and y are just our variables. They're basically placeholders standing in for quantities we just don't know yet. Now, let's scale things up a bit. Imagine you're fencing a rectangular garden. The length is L meters and the width is W meters. Wire fencing along the two lengths costs 100 rupees per meter. So that's 2 times L times 100, giving us 200 L. A wooden fence along the two widths costs 80 rupees per meter, which gives us 160 W. And finally, let's say you need special seeds for the entire area, which, remember, is length times width, and those cost 50 rupees per square meter. That adds 50 LW. Add all those pieces up, and your total cost is 200 L plus 160 W plus 50 LW. This is like a giant puzzle, and it brilliantly shows how algebra lets us create a hyper-precise formula for total expenses, no matter how massive or tiny that garden actually turns out to be. Expressions just let us turn physical dimensions into formulas. Section 2. Decoding polynomials, the language of math. All right, moving on. The absolute most critical concept you need to grasp here is the degree of a polynomial. Simply put, when you have an expression with only one variable, say we're just working with x, the degree is the highest power attached to that variable. Now, today, our entire focus is on linear polynomials. And the big secret to a linear polynomial is that its highest power is always an invisible 1. So when you see a plain old x sitting there, it's actually x to the power of 1. And this table here brilliantly illustrates the difference. Take a look. A linear polynomial, like 3z plus 7, has a degree of 1. If we bump that highest power up to a 2, like an x squared plus 5x plus 1, well, now it becomes a quadratic polynomial. If the highest power is a 3, it's cubic. Here's a pro tip for you. Do not let the number of terms confuse you. Always scan the expression for the highest little exponent. If it's a 1, you are for sure dealing with a linear polynomial. So, quick recap. Variables make expressions, and a highest power of 1 makes it linear. Got it? Awesome. Section 3. Solving equations. Unlocking the unknowns. Okay, time for you to do some heavy lifting. I want you to be an active learner here. Grab a piece of paper, pause this explainer, and try to model this real-world scenario as an equation. Ready? The sum of two numbers is 64. One number is 10 more than the other. What are the two numbers? Take a quick second to set up your variables before we walk through the solution together. All right, let's break this down step by step so we don't get overwhelmed. Step 1, we honestly don't know the smaller number, so let's just call it x. Step 2, the problem says the larger number is 10 more, so that has to be x plus 10. Step 3, their sum is 64, which instantly gives us our equation. X plus 10 equals 64. Actually, notice how the expression mathematically becomes an equation the exact second we drop that equal sign in there? Step 4, we combine our x's to get 2x plus 10 equals 64. Step 5, subtract 10 from both sides, so 2x equals 54, and dividing by 2 leaves us with x equals 27. If the smaller number is 27, the larger is 10 more, so 37. You see? Equations are just expressions set equal to a value so we can actually solve for x. Section 4. Linear growth and decay, patterns over time. Check out this table tracking the water level in a tank over a few months. At month 0, it starts right at 3 meters. At month 1, it's 2.5 meters. Month 2, 2 meters. Do you see the pattern emerging here? The water level is dropping by exactly 0.5 meters every single month. Because the quantity is decreasing by a constant fixed amount over equal intervals of time, this right here is a textbook example of linear decay. If it were increasing by a fixed amount, it would be linear growth. Pretty straightforward, right? Now, what's really fascinating about this next concept is that sometimes we have the data points, but we literally need to reverse engineer the formula. So here's another pause and solve challenge for you. A telecom company charges a fixed monthly fee plus a specific cost per gigabyte of data. 10 gigabytes costs 350 rupees, 20 gigabytes cost 550 rupees. So how do we actually find the fixed fee B and the rate per gigabyte A in our standard linear equation y equals ax plus b? Well, think about the difference between the two plans. An increase of 10 gigabytes results in a cost increase of 200 rupees. Therefore, each single GB, which is our A or our rate, has to be 20 rupees. If 10 gigabytes costs 200 rupees, the remaining 150 rupees of that 350 rupee bill absolutely must be the fixed fee, our B. To recap, steady, predictable changes over time or usage, that's your linear growth and decay. Section 5. Graphing linear patterns, seeing the math. I love to think of a linear polynomial as a highly predictable input-output machine. Let's take the function expression 2x plus 3. If we drop an input of x equals 4 into this machine, it mathematically multiplies it by 2, adds 3, and spits out a clean output of 11. If we input a negative number, like x equals -6, the machine does the exact same mechanical process. 2 times -6 is -12 plus 3, giving an output of -9. Every single unique input x absolutely guarantees a specific output y. And when we pair those inputs and outputs together, they form coordinate points. Let's look at a slightly simpler function, y equals 2x. If we plot the inputs and outputs, say points like -2, -4, 1, 2, and 3, 6, on a graph, a very, very clear pattern emerges. So the crucial takeaway is this. Because a linear polynomial always has a consistent, unwavering rate of change, plotting its points will literally always form a perfectly straight line. Listen, if you are graphing a linear equation on an exam and your line looks bent or zigzagged, yeah, no way, you instantly know you've made a calculation error. In short, linear polynomials always create perfectly straight lines on a graph. Section 6, Final Toolkit, Summary and Practice. All right, let's do a super quick rapid-fire recap. We learned that algebraic expressions are just combinations of variables, numbers, and operations, kind of like translating Raju's shopping trip into the language of math. We also learned that if the highest power of the variable is an invisible 1, the polynomial is officially linear. And finally, when we set one of those linear expressions equal to a constant or another expression, boom, we create an equation that we can actually solve for an unknown value. Now, here is your mental formula sheet. Keep this locked in. The general form of a linear relationship is y equals ax plus b. But I want you to really understand the meaning behind this, not just blindly memorize it. A represents your slope. It tells you the steepness and the exact rate of growth or decay. B is your y-intercept. It's your starting value when x is 0, kind of like that fixed monthly fee in our telecom example. Interestingly, if b happens to be 0, it means there's no fixed starting value, and your straight line will pass directly through the origin of your graph. Listen up, because here is a secret for test day to help you dodge the most common traps examiners love to set. First, do not confuse terms with coefficients. In the expression 4x, the whole thing, 4x, is the term, but the number 4 alone is just the coefficient. Second, always double-check the degree. Examiners love to sneak in an x squared, like x squared plus 5x, just to trick you. That is quadratic, folks, not linear. Finally, when you're graphing, just use your common sense. If your slope A is positive, your line should go uphill from left to right. If it's negative, indicating decay, it absolutely must go downhill. To truly master this whole thing, you have to practice. So I'm going to leave you with a classic end-of-chapter homework problem straight from our source text to really test your algebraic modeling skills. Salil's mother is 3 times his age. In 5 years, their ages will add up to 70. Grab a pen, set Salil's current age to x, build out their future ages, and set up the equation to find out how old they both are right now. Pause the explainer and give it a shot. Okay, if you calculated that Salil is 10 and his mother is 30, Excellent work. You completely nailed it. We've covered some incredible ground today, from the basic vocabulary of variables and coefficients all the way to the visual beauty of graphing straight lines. Mathematics is essentially the secret code of the universe. So I want to leave you with this thought. If linear polynomials govern everything from the cost of your monthly telecom bill to the dropping height of water in a tank, what other hidden linear patterns are shaping the world around you right now? Keep observing, keep calculating, and always keep learning. Thanks so much for joining me on this explainer. Catch you next time.